Swayam Prabha. Digital India. Educated India.
Welcome to the Advanced Digital Image Processing and Computer Vision subject. We are discussing about feature detection and description. So today we will continue that discussion. In the last lecture, I discussed about feature detectors, particularly the key point detector. So key points, the observation is that key points are those points where they are in the neighborhood. If you move around the neighborhood, you will have some changes in the statistics of the brightness distributions, and significant changes, I should say. And we have seen that there is an operator called Harris operator which measures these characteristics. That means actually what it does, it gives a measure which is proportional to the minimum possible change in considering every movement in every direction. So that gives itself a measure, and by that you can get those key points. So consider this particular problem where you would like to perform the registration or matching of pairing points which are of the same scene point. Say consider say this point around this, consider the point here, and similarly consider this structure. Now visually we can see that this point, say the joint of these two faces at the corner point, say this is the corner point. So this point and this point, they should be the same point of the scene. But can you compute, can you perform matching of these points? So one of the idea is that first you consider such points which are there should be a good probability that it occurs in both the scene. So you can find out. So it is very difficult to search. For example, I could have considered the neighborhood statistics around this point and make a search over the whole image at every point and try to see where this kind of structure is has the similarities, and try to say, okay, this is the point where this is a the corresponding point of this particular one. But there are various weakness in this approach. One is that it is computationally very intensive if you want to search the whole image, and the other one is that it may not be very robust. The kind of distributions you are talking about, there could be transformations for rotation, there could be three-dimensional projectional transformations. That means you have two different views of a camera. As it happens here, it is taken from two different views. There could be the scale changes. That means you are taking images from a distance, you are taking images a bit nearer. So this kind of matching problem is always is challenging. So first thing, rather, what we would like to do, that we would like to ensure at least out of all these possibilities, at least try to reduce this set where you have only a few number of points. Those are called key points in both the images, so that at least there exists a pair which should have certain correspondences. So this is the idea by which motivation by which these key points are detected, and we have discussed, say there are two stages of detection. First you apply the Harris operator and get the distributions of minimum changes, that measure which is proportional to the minimum changes at every point, and wherever this change is significant, we are displaying it through their brightness value, and after that you consider the local maxima. Now this is not very clear in this diagram, but I have shown, for example, corresponding to this pattern, there would be some structure here. You may see that there are certain points which is corresponding to that, because only one local maximum we have selected. So that's why it is not very much displayable. So similarly, for this image also, you get that set of points. So you have number of points here. Actually, there are a number of points, though it's a very tiny dots which are not visible. So this set of number of points. So just for the sake of the convenience, I am just showing with these crosses that now the problem is that which point corresponds to which point. You see that search space has reduced significantly to a great extent, only a few set of points. And now your problem is that, okay, this point may be matched with this one, this point may be matched with this one, like that. I mean, but how do you say? So that actually visually also they are representing the same visual content or the same structural points in the three-dimensional world. So for that reason, what we usually do, around these points, now around this point we make a local descriptor, and that description, once again, as I mentioned, a feature is mathematically described as a vector in a multidimensional space, multidimensional real space. So we want to get a descriptor which is also a vector in certain dimensional space for each of them. For each of them. Now those descriptors, considering its neighborhood statistics, they now become the identity of those points. Per se, point is just a location. So every location is like that. But the identity of the point is defined by those descriptors. They are feature vectors. So now you can see that what is the similarity between those feature vectors. For example, you can use any distance measure. In the last lecture also I mentioned that. And if you find that distance is small, then you see that there is a good chance that these two key points, they correspond to the same scene point. So that is the idea. And there are other ways that you try to take that pair which has the minimum distance. There are various strategies. So I'm just off the hand, I'm saying some of the intuitively, I'm just mentioning some of the strategies, simple strategies. So the as I mentioned, just to summarize this matching task, you have to detect feature points in both images as we see, then describe them by local statistics and find corresponding pairs. That is the matching task. So now actually what we will be discussing, how to get a description around by exploiting the local statistics of the neighboring region around a point. So we are first discussing with respect to point. These concepts should be again extended for small patches, even for the overall image, so that in its own context, it represents the visual content restricted to that particular part or that particular structure of the image. So what are the considerations when we design such descriptor, which means the computational technique to get this description? First thing, that it requires certain kind of some invariances. Suppose we apply certain transformations, as I mentioned, various transformations, translation, rotation, scale change, even the view change, whether these descriptors will remain almost the same, then that is the objective. They should be very close. Those descriptors should be very close. It won't be the exact, exactly equal, it won't establish the exact equality, but since these are all numeric values, so it should be very close to those numeric values of the feature vectors. In the feature space, I should say distance should be very small. So these are certain kind of invariance we expect. There could be rotation, there could be change of illumination, there could be change of scale, etc. But one of the major challenge is that scale invariance, because that is very often, particularly in the case of optical imaging, through ordinary camera, optical camera. The thing is that the object could be nearer, very close to the camera, object could be taken from a very far away. But suppose the same structure is visible even in the close vicinity and also in the far away. So, how do you get a descriptor of that structure so that even due to the change of scale, still it will establish the correspondence. Now, that is one thing, and the problem is that even the structure, the local descriptor, it changes. It changes with with scale, though it is the same structure. I am just giving one example. So we say that at which scale this description is made. So the scale invariant detection is not that you get a descriptor which remains the same for every changing scale. Rather, it is not possible. Every scale there is some kind of details which is which will be quite different from the details which is present in other scale. Say you consider an image, there would be some examples, I will later on explain this part. So this is what, but the question is that when you have such key points, but can you consider for that same key point, can you consider multi-scale descriptor? So that is the idea. That means at every scale you can get some descriptions. So the multi-scale means, say I have an image here of certain dimension. This is my input image. That is the resolution set by the imaging device. Now I cannot increase the resolution. I can computationally increase, but physically I cannot get higher resolutions because that is the sensor driven resolution. So, but what I can do, I can decrease the resolution. That means I can downsample it, this image, I can downsample at various scale. So I will basically reduce these points. I will get a downsampled version. So you consider that Gaussian pyramid representation, same thing. So you just downsample them and you have multiple resolution of the same scene. So your highest resolution is the given image, but as you downsample, you go for lower resolution image. So, but that gives the scale variation of the image. So every scale, then you consider if the key point exists in those scales also. Now it's neighboring statistics at that scale you observe. So you have multiple descriptors. For the same key point, you have multiple descriptors. So the matching problem remains something like that, that if you have a key point and key point should be considered in multiple scales with multiple descriptors of those key points. Now you try to match that at which scale these are appropriate. So you try to consider the respective scale when this descriptor should be considered. At that scale, that is the descriptor should be considered. So and then while matching, there is a probability that in some scale you will get a good matching and you can declare those 2 points are similar. So that is the way the scale is handled. You should have redundant description of the same key point at different scales. And the computational idea is also simple, that you just downsample. Downsample is as I mentioned, you just filter it using some low pass filter and then downsample because of avoiding the aliasing effect. So let us just proceed with this kind of explanation. So what we require, that in the scale space we require a local maxima. So the question is now that I can have multiple scale, but for a feature there is an appropriate scale at which you should get the descriptor. To reduce the redundancy, we are not taking the features description at every possible scale, but what we consider that there is a scale where these local changes, that f, that the Harris operators measure, which we discussed, where it is local maxima even across the scale. So it is not only local maxima, say earlier when I have a single image, when I am taking the distribution of f, so I am considering a local maxima as the key point. But now I will consider a three-dimensional space. That means I will have multiple scale representation. I will downsample them, right? I may not have the Gaussian pyramid structure also. Just I should downsample and take the local maxima, so that each point corresponds to this point, corresponds to this point. So in this space, so I have it. We call it scale space representation. So you have a scale, say, since we are filtering with respect to certain say weighted function, say Gaussian mask. So standard deviation sigma, which could be the measure of the scale, and you have also the spatial directions, like say this is say y and say this is x. So this is a kind of three-dimensional space, x, y for the image coordinates, spatial coordinates, and scale is the representation. And it's just, every scale you are again computing this measure f and find out local maxima considering this three-dimensional space, just not the two-dimensional distribution. And that is how the key points at a particular scale. So for that key point, that is the appropriate scale where it should be described. And it goes like that. So every key point is associated with certain scale. So in this way, you are pinpointing that which scale this key point should be there. For example, in an image, say I have a corner. In both the images, I have a corner. Say this is a corner with the larger scale because it is nearer, and this is a corner, say larger means, say in this case, it is basically high resolution image, and this is a corner with a coarser, lower resolution. So we say that higher scale means lower resolution. So this is larger scale object, and this is lower scale in that sense. Now the question is that when this point and this point is there, so at which scale this should be described? These neighboring statistics, they would be quite widely varied. But what I would do, I will perform multi-resolution representation of both the images and then take the local maxima of the three-dimensional representation, that scale space representation of the images, and from there that descriptor and that scale of this point will be considered. For this also will be considered, and since they are now represented at the best scale where they are representable, because of this local maxima we expect there is appropriate descriptor, so they should have a good match, and so we will only consider that description. So one of the definition of f is that so I discussed Harris operator, but we can consider also Laplacian operator. So the Laplacian measure also can be a measure. That Laplacian is the double derivative operators in two-dimensional space, which means that suppose I have an image function, say brightness function, say I x y. So what I would like to measure double derivative of this and double derivative both in x and y direction and simply add them. So this is the Laplacian measure of the image at any point x, y. Okay. So this we can measure. So this could be one possible measure of these operations. This is also trying to measure that similar to Harris operator. It is trying to measure that change. Or what we can do, the difference between two Gaussian filtered images with different ASTs. That means so in the scale space representation itself, so in the Gaussian pyramid representations I have earlier mentioned, what we do that I have a image at a particular resolution, then what I do, I filter this image with a Gaussian filter of certain scale sigma. So now you take the difference. So you take the difference, right? You take the difference, and whatever thing you get, that is the difference of Gaussian Gaussian filtered, no, between two Gaussian filtered images. We say this is the difference of Gaussian operator. So the resultant image with these operations, what you get, this is the image you get from the difference of Gaussian operator, where the parameter is this sigma. So you, by varying sigma at every scale, so from here again you filter this one, so you get a pyramid representation. So from there again you take another sigma step and you get another difference of Gaussian. So you get a stack of difference of Gaussian operated image, and that's the multiscale representation. And there you find out the local peak, local maxima of that space. Like in this direction you have sigma, in these directions like the images x and y, the way I am showing it. So we may consider either Laplacian operations at multiple scales, or you may consider also the differential operations. So it says that now what is meant by this invariance, just to say that now if I have two images I1 and I2, and if I2 is transformed version of I1, and I have already mentioned these may be different kinds of transformation. You can see there are various other things I have added, like reflection, non-uniform scaling, illumination I mentioned earlier, view also I mentioned. So there are different types of transformation which are possible, and we would like to have invariance in our descriptor. So transformation invariance, it means that is a property of a detector which could detect the same features regardless of the transformation. So for making it to be invariant, now it should be ensured that detector to be transformational invariant. So this should be one property, like Harris measure is invariant to translation and rotation, but it is not invariant to scale. And scale requires handling of multi-resolution representation, as I mentioned. So usual approach would be computing features at multiple scales using a Gaussian pyramid. Just now I explained a bit more, I will elaborate it further. So more precise computation locates features at the best scale. So there is a very popular and powerful feature descriptor which is called scale invariant feature transform. In acronym it is SIFT or SIFT. Now this is a very widely used operator. It has been found, it is very robust, and many applications we use it. So I will describe this operator, these computations following this particular discussion. So feature descriptor should be transformational invariant. So first is detection should be transformational invariant. Also your descriptor should be also transformational invariant, because by making detection transformation invariant, you are ensuring the presence of the points which have the correspondences. So at least those presences are there. You are ensuring that out of all my possible candidates, there exists at least one which will have a correspondence with the point of the base image. Say I consider one of them is a reference image where I have set of key points, and say this is my respective I should say target image, and we have a set of key points. So detection, so through detectors we have detected these key points, but we ensure that for this point, out of this candidate there exists one which is similar to this. We ensure for all the things, I mean at least most of the points. So this is the this kind of guarantee if we can put, or intuitively this guarantee if we put, then we say that this detection is also transformational invariant. Because of transformation also we can ensure this property. So that is about the detection. Similarly, as I on the way of my building correspondences, I will be using descriptors as I mentioned. So what is the descriptor around this point? What is the descriptor around this point? Similarly, what is the descriptor around this point, around this point? Now again, if this point corresponds to this point, so these descriptors should be also transformation invariant. Ideally, it should be transformation invariant. There would be certain tolerances, certain variations, small variations, but ideally we want it should be transformation invariant. So that is the part. So it captures the information in a region around the detected feature point. And there are different kinds of no way you can describe these statistics. One of the thing is that mostly you will find in most cases it is the gradient directions that is considered. So, which statistics? It is not the brightness values, rather change of brightness values. So, the directions, gradient directions, you know that directions at which the change, maximum change takes place. So, these directions we are considering. So, you simply take the gradient along, say if I have the image we have discussed earlier also, I have to take the derivative with respect to horizontal direction, say x axis, say horizontal axis if we consider. Similarly, I have to get the derivative along the y axis. Now, this becomes my vector and it has a direction. Now, this direction is mostly considered. So, which means certain angular direction, certain with some reference, its angular directions, it is considered with respect to certain reference axis. And we build up the statistics, distributions that you can beam those directions, get a histogram, and that becomes a feature vector. So, we will see that how this is done in subsequent discussion, right. So, when we are find the key points, we have already get the location, and the scale, as I mentioned, for scale we have to get the local maxima in the scale space. So, from there you also get the scale, and if you around this point, if you get the dominant directions, so you get a direction. So, different level of information, different types of information that you can tag with respect to your key points. So, let us try to understand the operations on scale. As I was telling you that there are certain appropriate scales where those descriptors are more meaningful. Say, consider this image. Now, consider a part of this one. Consider this particular zone. Now, you can see something is written there. Now, this may not be readable if you are at a very far distance, but this content that. So you see that the local variations, etc., those kind of things are not very perceptible, and that's why you cannot read it. Like from the scene also you may not be able to read it. Now, if I increase this particular scale, that means what I considered, I zoomed this. So I am going in the reverse direction for the sake of example. Though in actual computations we start with the higher resolution and go to the lower resolution, but I am just interpolating. So, I am just zooming. So, if I consider this, actually I did not do any interpolation, I just displayed this structure in a larger area, so that it gives the effect of the higher resolution effect of this, because this area now you can see that every pixel has a higher representing a I should say smaller area in the original scene. That is how the resolution gets. Now, you can see that this words probably is visible, something like as you can see that this one is L, this one is A. So, you can distinguish. So, L, say A, you can distinguish alphabets, and then you can read the thing. Further zooming of that side, I mean, with increasing high resolution display of the same scene, these are becoming more visible. But after that, if I really go on expanding, say this region, then the structure will not come. So this is for example, this could be the maximum, or this could be the maximum resolutions where it should be represented properly, these features. So, the scale invariant detection, what we do that, and as I mentioned, that you have to perform the difference of Gaussian operator and then take the local maxima in the scale space representation of the image. So, you can see I have already shown the function, that the Gaussian function with the parameter sigma, because this is a parameter. So, with varying sigma, I can get this kind of filter. So this function is providing you the impulse response of a Gaussian filter. So at varying sigma, you can design different Gaussian filters, and then you can apply on the image. That means you can convolve the image with these filters and you get multi-scale representation. And not only that, what actually you are interested to do here, you take the difference. You take the difference between two subsequent or two adjacent images in that scale space. That means you apply sigma, then 2 sigma, say 3 sigma, or certain factors of sigma. So whatever images you are getting, take the difference, and that is the difference of Gaussian operator. So adjacent images, those differences you are taking. So convolve with image and observe extrema in 3 dimension. And so there could be different kinds of kernels, as I mentioned, Laplacian kernels could be there, and difference of Gaussian kernel could be there. So this is a Gaussian part. And for Laplacian kernel, this is a form of the Laplacian kernel with the scale space normalization. This normalization is there because we can show that these two are, in that case, they are equivalent computations. That is how this normalization is there. But as you understand that if sigma is constant, so finding out local maxima, it does not have much effect. Only you are computing. This is exactly the Gaussian Laplacian operations. As I mentioned, this xx means double derivative. So what we are doing here, we are taking the Laplacian operated images. So let me write in short form the images I. So this is the Laplacian operated images, and then you are convolving with the Gaussian mask, right? So that is what you are computing, but effectively it can be shown that instead directly I can convolve with the Laplacian of Gaussian mask itself. So let me put sigma as the parameter. So Laplacian of the Gaussian function itself. So they will provide me the equivalent result. That is the property of the Gaussian functions that we are using here. So I just shown here the function for difference of Gaussian. You can see that here you have filtered with the parameter sigma. This is the so same thing, like you can consider Gaussian filtered images and take difference, or you can use this filter with this function and then convolve it with the image. That would also give us the same operator. So that's why this could be considered also as a difference of Gaussian operator, because it can be proved analytically that by exploiting properties of Gaussian functions, you can establish those equivalences. So theoretical equivalences you can establish. So some of the kernel plots, we say that in one dimension. So just one dimension Gaussian function we know, and if I consider this and we plot in one dimension, you can see that the Laplacian Laplacian function is quite similar to the difference of Gaussian functions at a particular considering those equivalent suitable parameters for both of them. And this is the relationships I was mentioning, that how Laplacian of Gaussian operator and difference of Gaussian operator, they provide similar results. So this is the theoretical analysis. That means the Gaussian functions, if I take derivative with respect to the parameter sigma, while sigma is the standard deviation, as you know that for the Gaussian function, then this is equivalent. This is same as if you take the Laplacian of Gaussian function and multiply with the sigma. Because of this, we can show that how these two are giving you the proportional values. So the difference of Gaussian operator gives the proportional value of the Laplacian operators. Okay, so this is how the both are giving similar results. So just to once again elaborate that further, that scale space representations, So what we do, we perform the scale space representation at different scale, but you can see that some pragmatic scheme has been used. First, you have used certain resolution, spatial resolution of the image, and keep the same spatial resolution and apply the filtering of with sigma. So this image you apply Gaussian filter with sigma, say this image you apply Gaussian filter of say 2 sigma, say this is 3 sigma, and in this way you can go up to 8 sigma. That is the first octave, and you just take the difference. Okay. So this gives you a difference of Gaussian space operator, and you take the local maxima out of it. Suppose this is the local maxima considering this neighborhood, 3-dimensional neighborhood, so this would be one detector. But this scheme can continue with a large number of scale values. But what we do for the sake of computations, it does not make any sense if it is filtered with a large sigma, then almost you will see constant values. So you will find kind of this zone, all of them will be of same kind of functional values if you consider this resolution. So instead of computing on that, why don't you downsample them? They take them only 1 pixel. So that's what it does in the next octave. First you downsample it, and then again you apply the same operations, and you can go for different octaves. And the whole stack will be giving you this kind of multi-scale representation of the difference of Gaussian operator space. And there you are detecting the key points. So when you detect the key points, what you are getting a location. So location is as you understand, so this is x and this is y. So the coordinate at this point, and also you are getting the scale. So in this case, this is the scale. So you are getting both location and scale while detecting this key point. So I am describing the shift algorithm. So this is what the shift detector is acts, how it operates. So I just mentioned this. So you have to find extrema in 3-dimensional difference of Gaussian space. So some of the typical examples, if we see this kind of scale space representation, say you consider octave 1, and that means few scales we will be considering. Say I will be using, though I am saying octave, actually I will show only few, say 3 samples. Say this is the sigma is 2 to the power 2 by 3, and these are the difference of Gaussian image what you see. If I use increase the sigma, it will be coarser. So the edges you will see they are getting coarse and blurred. If I use sigma equal to 2, this is a representation. In the next octave, once again, I will be downsample it, as I mentioned, many of the values are same. So I will downsample and I will apply larger scale. So it goes like this. So this is octave 3. These are certain examples that, so you see that this is a scale space representation, and now you take the local maxima in this representation. So this is one example. So you see lot of extrema point is there. So what you should do, that you consider most robust points. So actually many edge points are also coming. So if you remove them, then you will get further reduced set and which are more robust. So that's why first thing is that edge points needs to be removed, and locations also may not be accurate, and for that you have to consider certain things. So one of the operator which is used for eliminating edge points, that is that Hessian operator. So if even in Hessian operator, actually what it does, through Hessian operator you can capture the curvatures. You can capture the curvature around the 2-dimensional space. So it's a 2-dimensional function. Suppose you have a functions in a 2-dimensional space. So I'm just showing it's a 2-dimensional space. So the curvature, that if it's a 2D curve, a curvature measures that how the this curve is basically there is a definition that tangential angle basic definition of curvature, you know that if I consider the tangents, how their angles are changing with respect to the length of the curve. It's a delta length, what is the angle change? So, if the change of angle is d psi and ds, that is the curvature. So, it shows also how this angle is changing, how the tangent is changing or normal is changing. But in two-dimensional, in a three-dimensional space, actually it's a surface. If I consider a surface, then what we do actually, we take many such two-dimensional curve. That means we take cross-section or planar cross-section of curves, and for each planar curve we can measure this curvature. Then you get a curvature for different directions. So, these are the tangential directions. So, this plane, I can say that no, around this point there are certain directions where actually the curvature would be maximum and minimum. So, Hessian matrix can give me those two directions and two curvatures. So, it can ensure that, like the previous case of Harris operator, minimum change and maximum change, instead the changes it considers the curvature. So, minimum curvature and maximum curvature. So, what we want, like now, as I mentioned, not an edge point but a corner point. So, there we want both the curvatures should be significantly high, same condition, which means that minimum curvature should be strong. Again, that eigenvalue analysis, those things we do, but instead of eigenvalue, you know that the similar considerations of product determinant of this matrix H and also trace of H, those can be used to get this kind of measure. So, that is what is used here when we consider to eliminate some of these key points. So, edge points are large principal curvature across the edge, but a small one in the perpendicular direction. So, the eigenvalues of H are proportional to the principal curvatures. So, two eigenvalues shouldn't differ too much, and no, this is what I was mentioning, that determinant divided by trace, instead of I did the opposite way, trace H divided by determinant H. So, this value should be low. So, for high value of R, it should be less than this, it should be less than this value. So, only we take those values, those points whose value is less than this. So, if suppose 10, which means this value is 11 square by 10. Say, if I put R equal to 10, it is 11, so it is 1.21. So, if the value is less than 1.21, then we accept those points. So, we eliminate key point if the ratio greater than this threshold. So, just an example, say this is the initial set as I have shown in the previous example. This is my initial set, these points, and if I apply this ratio threshold, which is based on this curvature test, we can reduce significant number of points. So, we can consider good robust key points, their position and scale. Now, another thing we would like to assign, that what is the dominant orientation. So, for that, as I was mentioning, that we can create histogram of local gradient directions at a particular selected scale. So, once you have selected scale, now you consider in that scale only you will be measuring those gradient directions. That is important. That is why scale selection comes first. After key point detected, immediately scale is also assigned. Then you consider only the descriptions at that representation of scale. That means that filtered image you should consider from the original image, not the original image, it is that filtered image. And then apply the local statistics. So, you get the local gradient directions, and there you can see here that say this is the B. So, you are doing some binning here. Basically, it is a continuous space. So, you can have some binning of certain. So, you can have 8 number of bin, you can have 16, 20, whatever, and you roughly consider that which is the gradient direction where the histogram is maximum. Where is the maximum of the histogram? So, you take that is the gradient directions. Now, it may not be unique, you can have multiple directions, and you can smooth the histogram to get the peak. So, as I mentioned, if there are two major orientations, you may use both. So, for a key point descriptors, for each key point has a location, scale and orientation. So, next is to compute a descriptor for the local image region about each key point that is highly distinctive and also invariant as possible to variations such as changes in viewpoint and illumination. So, with this just let me describe how this descriptor is computed. So, there is a specific computational I should say recipe that is proposed by the inventor David Lowe and as you can see his also colleagues, and it is published in ICCV, and it is called scale invariant feature transform. So, what it does, so through empirical experimentations, these are the things they have found, and this is how this descriptor is used or computed. So, first you take a 16 cross 16 square window which is orientation corrected around the detected features. So, orientation corrected means that you got the dominant direction. So, with the dominant directions you perform a rotation centering that key point, and now with that rotation whatever square window you get, you take the gradient directions with respect to that only. So, your horizontal direction will change because of the orientation. So, that is why the orientation correction is very important, and there the dominant direction orientation is used, and also the scale descriptor there the scale is used. So, this is how orientation and scale is used and position is used, because those are given to you, and then you get this multidimensional representation. So, now you compute edge orientation. So, angle of the gradient minus 90 degree for each pixel throughout weak edges. So, once we compute this edge orientation, we should provide some kind of edge, some kind of decision which are the edges, which are weak edges we should throw out. So, which means that we can threshold using the gradient magnitude, and now we can create the histogram of surviving edge orientation. Now, it could be weighted histogram also, which means this gradient magnitude also could be counted, could be used for forming this histogram. So, that is also considered. So, for a shift descriptors, what we do that divide the 16 cross 16 window into a 4 cross 4 grid of cells. For the sake of convenience, we are showing it a 4 cross 4 block with 2 cross 2 divisions, and for each 4 cross 4 grid cells you form the histograms of 8 orientations. So, in 4 cross 4 grid cell you have a 16 cells. So, finally, you get a 128 dimensional descriptor. So, that is how the feature vector is described in a multidimensional feature space. It has been found that this descriptor, shift descriptor, it is very robust and it is capable of handling changes in viewpoint and also significant changes in illumination. A little more qualifier through experimentation, it has been shown that up to about 60 degree out of plane rotation it can consider, and significant change in illumination. So, even the day and night. So, that variation also it can handle. Now, shift is a very computationally intensive feature descriptor. As you can see that the Gaussian smoothing is quite computationally intensive. Gaussian masks are large. With larger scale, you should have larger mask weights, and that is the key computational I should say load, this kind of Gaussian filtering. So, there are so that is why there are efforts by which you can reduce these computations by replacing, instead of Gaussian filtering, some other efficient filtering. At the same time, you get similar kind of performance, because your purpose is to take the scale space representation by doing multi-resolution representation of the image. So, or rather there are other ways that difference of Gaussian operator what it is producing, whether I can compute that similar equivalent way with maybe with certain trade off, with some compromise, but with much reduction in computation. So, one of this technique which is speeding these operations, and these features, descriptors are called speeded up robust features, or SURF, that is the acronym, which is also quite popular. And as you can see that it is reported in ECCV in 2006 by the respective authors. So there the Gaussian filters are replaced by box type convolution filters. So box type convolution filters means that in this case, as you know that filter responses, usually their impulse responses are shown by masks, and the masks and there are weights. So for example, I can put some weights, say 2, 3, 4, 6 like that. So there are some weights, and then these weighted averages are used. I mean, you can make the sum of the weights or whatever proportional value would give you the filtered image. But box filter means actually some of these weights are same. So this region, say this weight is same. Say this region, this weight may be -2. So this region, this weight may be say -2. This region say, which means in a box filter, certain rectangular patches, they have constant weights. So it looks like a box. So and it has certain advantages. So as you can see that when we are doing box filtering, what I can do, I can simply sum these pixels and multiply by 2. That is what is the effect of computing with this region. Similarly, sum these pixels, so this pixels, and multiply by -2. Now, this kind of advantage you have if you have box filter, and in fact, these computations could be further enhanced by using integral images. That means one time you compute an image which is called integral image, and the results of those integral image, so functional values at every locations, they can be used. So I will be explaining that part, how integral images can speed up these computations equivalently. It will be clear to you later on. But these are certain tricks which are used to speed up the computations. The other thing is that instead of difference of Gaussian, it uses the Hessian operator for key point detector. So earlier also I mentioned that Hessian operators could be used for key point detectors, because Hessian operator is also equivalent to the difference of Gaussian operations. So which means actually local maxima of determinant of Hessian operator, that is being used in this case. So accumulate orientation corrected. Also, for the gradient computations, it used the Haar, instead of gradient computations, it used Haar wavelet responses. So, there your feature, it's not considering every possible gradient directions. Rather, it is considering certain fixed directions. So, Haar wavelet responses is designed in such a way that it's equivalent to finding out changes in say horizontal directions, changes in vertical directions, or changes in say diagonal directions. Say it's 4 directions. So in this way, it reduces also the number of directions, number of computations. So these are few things this SURF operator does. So if I simply just illustrate them. So this is a Hessian operator. You can see that it is the same Laplacian operator, but Laplacian with a scale. So this is the convolution with Gaussian second order derivative with image. So this is how it is done. So key point is maximum of determinant H over space and scale. That is the computation it carries out. Now actually this convolution, though it is Gaussian, but we will see that equivalent computations using box filter, they are using. So that is what it is described here. So if you are computing DYY, that means say vertical directions, so you take this kind of weight distribution. So as I mentioned, rectangular patches with a constant weight. So this is the rectangular patch in that filter zone. So they are multiplied by 1, which means you take the sum of these pixels. Similarly, you take the sum of these pixels, and you take the sum of this pixel multiply by -2, and then you just simply add those 3 values. That is what will give you the equivalent to the somewhat approximation of this double derivative along the y directions with a Gaussian filter. So, if you increase the scale, which means if you increase this size, the scale will be increased, and this is for dxy. In the same way, if I look at the horizontal placement of this rectangle, it will be dxx, which is not shown here, and then you can compute the determinant in this fashion, and this w is roughly 0.9, and this 9 cross 9 box filters are approximation of Gaussian width of 1.2. So, these are certain things empirically it has been established and it has been shown. It can be shown also theoretically. There are theories by which one can show that how repeated smoothing, uniform sampling, uniform smoothing, smoothing with an uniform kernel can perform equivalent near about Gaussian. So, it is a central limit theory which can be applied to understand this. So, I am not going into details, but if you are interested, you can. It is a very interesting topic how Gaussian filter can be approximated using kernels of uniform impulse response. A step. Yeah. So, let me just give you a little bit of idea of the integral image. So, this is the definition of an integral image. So, you can see that definition is that if I consider an image, so at every point, say this is the point, the value would be the sum of all the pixels of this rectangle starting from this point. So, this is what we are computing here. So, if you compute for all the points, that is integral image. The advantage is that suppose I want to compute the sum of this zone, which is required for box filter. What I will do? I will take the value here. So, once I have computed integral image, then I will simply compute these values minus this value, add this value. So, you can see that actually this value means I am taking sum of this area. This is the value around A. So, this value means I am taking sum of these areas, and these values means I am taking sum of these areas, and these values mean I am taking sum of these areas. So that if I remove the intersection part, only values which will be written only once, this is the sum of these values. So, you can just check it, and this is that equivalent computations, and it requires only 3 additions and 4 memory accesses. So, for Haar filter responses, you are considering Haar wavelets in dominant orientations only you do. So, this is for as I mentioned, gradient along say horizontal directions and vertical directions with a larger filter scale. This also is implemented through box filters. So, that is the advantage, and for example, it is required 6 operations. And finally, when you are considering accumulating the statistics, only those filtered values. So, these are the values. So, sum of those horizontal gradients, sum of the magnitudes, some of the vertical gradient, some of the magnitude. So, that is what you are doing. So, partitioned into 4 cross 4 square subregions, and then compute for each subregion these are the values. Responses are regularly spaced 5 cross 5 sample patches. So, each subregion has 4D vector. So, we have 4 cross 4 square subregions. So, 16 into 4D, 64D, and size of the window is 20 cross scale. So, in this way, SARP will give you a 64 dimensional vector instead of Shift, which gives you 128 dimensional vector, and SARP is also found to be quite robust like Shift, but computationally less intensive. So, with this, let me stop here today, and we will continue this discussion in the next lecture. Thank you for your listening and questions.